left of it, hopefully. I did run over there. Excellent suggestion to get some hot pizza while it's still hot, at least. But cold pizza is just as good. Right? Reheated pizza is not good. That's why you get yourself a toaster oven, right? Never microwave pizza, right? Always toaster oven. Anyway, we were talking about stacks last time, and we've seen them before. They're a LIFO data structure. That is, the last in is the first one out. Make sure that's working. Yeah, there we go. So if you have any questions, go ahead and post online to the live stream. Otherwise, the two operations that we usually associate with a stack are push. You put something on top of the stack, and then pop, you remove something from the top of the stack. Remove the thing at the top of the stack and retrieve it, right? So usually it's visualized like this. Why? Because it's kind of like the dish mechanism in a cafeteria. You push a plate down onto the spring-loaded mechanism on the bottom because you don't want these giant stacks of dishes that nobody can reach. As you pop one off, right, there is a little tab there that holds them in. As you pop it off, right, then the spring-loaded mechanisms pushes the rest of the dishes up. So if we were to put these in this order, there's Jackie right there. He gets put in at the bottom, right, because it's an empty stack initially. And then here, this is LeBron, right? There we go. LeBron goes in, and he's now at the top. Who's 23? Jordan and LeBron, but there we go. All right, so now Jordan is at the top. So if we start popping things off the top, they're going to be in the reverse order. Jordan comes off first, and then LeBron, and then Jackie there, right? So that's why we call it a LIFO data structure. The last one in is the first one out, right? It's not a line, right? For this reason, stacks are known as restricted access data structures, right? In contrast to this, collections like, say, lists or sets, right, or even maps, these are unstructured. Right? They just hold stuff, right? Now, a list, you can do something extra with a list, right? You can sort a list. You can impose on a structure on a list by sorting it. But sorting imposes an order, right? Sorting imposes on ordering, or structure on the state of the list. You can always, after sorting it, you can come and muck it up, right? You can add stuff to an arbitrary location. You can remove stuff. You can shift stuff around, swap stuff, do whatever, right? The basic CRUD, create, retrieve, update, and destroy. So there's not really an ordering in that sense. You can sort it, and it's good until you screw it up, right? But a stack is different. Its structure relies on its behavior, right? A stack's structure is in its behavior, right? You are not allowed an arbitrary, okay, now we're back on the live stream, arbitrary access, allowed arbitrary access to its structure, right? And so it's in its behavior. And as we've seen from object-oriented programming, right, there are three things to an object. There is its state, its behavior, its interface, right, the functionality that acts on that state, and then of course the grouping of those. Identity is the other thing, right? But that's not relevant here. So a restricted access data structure imposes an ordering on the collection's behavior. Right? We really like structure. Why do we like structure? Structure can be exploited, right? We've already seen this in Computer Science 1. If an array is sorted and we want to search through it, what kind of algorithm can we employ if it's sorted, if it has structure? Binary search. That gives us an exponential speed up in its behavior, right? So if you have a structure, you can exploit that structure for data storage, for fast algorithms, right, et cetera, et cetera. So again, a stack is a restricted access data structure. Let's go over here and create a stack. Right? So new class. I'll immediately go ahead and parameterize it so that it can hold anything, not just basketball and baseball numbers, integers, but it could hold doubles and strings and whatever else. Right? Ideas on how to get started. Hint, do not reinvent the wheel. This entire module is lists and list-based data structures. So what object-oriented programming principle could I bring to bear here to create a stack? I could think about inheritance, right? I could say extends one of my lists, extends list, whatever. Does that sound right though? Should you be able to do whatever you want with a stack, including say, or my list? Let's see, my list. Let's go to what that looks like. Should you be able to add an element at an arbitrary location, like add element at index? That doesn't sound like a stack to me. Being able to take something and insert it here, right? All your dishes are gonna fall. Right? That's not a stack. So inheritance kind of fails me. What's another object-oriented programming principle that we've talked about? Not one of the big four, but one of the others that you've used basically since seeing the first structure in CS1. Composition, exactly. So what if we had a private, and I'm going to go ahead and throw away my implementations immediately, and I had a private, list of elements, right? And I'll call this elements. Again, I've thrown away my list implementations. Why? Because the Java ones are better, right? They have way more features. So now let's think about the interface to this. I'm going to have a public void push method that takes in an element x and adds it to the top of the stack. And I'm going to have a public tpop function that retrieves and removes and returns the element at the top of the stack. So let's just go ahead and document those. Right? Adds or pushes adds the given element x to the top of the stack. Now, is there really a top or a bottom? Not really. Just take your computer and flip it upside down, and now the top is the bottom, bottom is the top, right? But we will need to think about that in terms of actual implementation. And the pop operation here is going to be removes and returns the element at the top of the stack. All right, there we go. Good. So now everything is in terms of this list over here, right? Which I still need to implement, but we'll come back to that later. So how do I add something onto this list? Let's think about this in terms of, say, a linked list. If you had a linked list that looks something like this, right? Something like that. What's the top and what's the bottom? It's horizontal. There's a beginning, there's a head, and there's a tail, right? Okay, fine. Let's cut this, paste it, and change it. There you go. Now it's vertical. Now can you tell me what the top and the bottom is? What's the top? Okay. Oh, this was the tail, right? Tail is equal to the top. The head is equal to the bottom. It doesn't really matter. If you want to, you can go ahead and flip them around, and it's the same thing, right? Okay. What if it was an array list? Oops. Here's your array. Dot, 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 dot. What's the top and what's the bottom? What again if I flip this up so that it was like this instead? Maybe the beginning, index 0 is the bottom, and then whatever size -1, there's your top. Right. So we could use a linked list or an array-based list. Let's think ahead here to efficiency. Which one's better? Which one was more expensive or less expensive based on our experiments from before, which I've gotten rid of, unfortunately? You can make them both efficient, but let's think about a linked list. If you're always adding something to the beginning and taking away something from the beginning, and you're keeping track of the head, that tells me that each one of these operations could be just, immediate. All you're doing is removing the head element and then adding a head element, right? By the way, a linked list implementation equals new linked list. Again, I'm abandoning my implementations here, and I'm going to start using Java's implementations. Let's take a look at what it looks like. I don't know if we looked at it before, right? But let's come up here and you tell me, what kind of a linked list is it? I see a first head, and I see a last, a tail. In other words, it's keeping track of both ends. Operations at both ends are efficient. That's good. What does this node look like? It has a next and a previous and an element. Ooh, wow. That was like ours, except for we didn't have a previous. What kind of a linked list does that tell you that this is? You can go forward and backwards. That's a doubly linked list, right? Wonderful. I've got all those bells and whistles that I really wanted without having to work for it. Right? I'm going to use that linked list. Now, in terms of that linked list, how are we going to push something onto the top? Do you want the top to be the beginning or the end? It doesn't matter because we're keeping track of both the head and the tail like I just showed you. Votes for the head. Oh, okay, votes for the tail. Oh, wow. I have no idea why you want that preference, but elements dot add. That adds it to the end. There we go. That's it. Now, what about our pop? Elements dot remove. Element at what index, though? This dot elements dot size -1. Good. Right. And return it. That's it. That's all there is to it. And we brought to bear the power of composition. That we are taking this one object, this one type of object, wrapping it around what's called a thin wrapper, right? So that we can change the interface. Push, pop are done in terms of that other data structure over there. We don't have to reinvent the wheel, but we do not lock ourselves into an inheritance hierarchy that doesn't make sense. Because a list is not a stack and a stack is not a list. Right? This is wonderful. Let's test it. So, stack s for integers, s is equal to new stack. There we go. S dot push. Right? Can I add to an arbitrary location? Add to index foo. Right? No. Why? Because I've only defined public methods that allow you restricted access, push and pop, one end and one end only. S dot push 10. Oh, you know what? Let's see. There we go. S dot. That was LeBron, right? I'm getting into basketball slowly. I don't know why. Right. There's Jordan. I don't know. Kobe. Kobe is or was 24, I think, right? At the end, right? S dot push. Now I'm out of basketball. Stars. What was Pippen? Scotty. 10? I want to say 10. I'm not sure. Anyway, there we go. What does the state of that stack look like? If I were to visualize that, what would be at the bottom? The first thing that I put in there, 6. What would be at the top? The last thing I put in there, 10, Pippen. Right? So let's go ahead and pull that stuff out. System.out.println s.pop. There we go. We're going to pop, 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 pop. What order am I going to get those in? In the exact reverse order. 10, 24, 23, 6. Right? Ah, I know. Let's test this. What if, because we're trying to break it, right? What if I popped from an empty stack? I don't know. Let's draw a picture. Okay. Not a parabola. I have to be very careful. Okay, whatever that is. All right, there's my stack. What would you expect to come off the top of the stack if you popped from it? Null? Okay. So let's go ahead and run this and see, do we get null back? No, we do not. What? Wait, an index? A linked list? What the hell is this? What are these things? I'm working with a stack here, right? But this error message is telling me something about a linked list and indexes and stuff like that. Do you see any indexes here outside of the class? No. Leaky abstraction. They've leaked information about how we've implemented this stack out to the outside world. Let's take care of that. If you pop from an empty stack, right? If this dot is empty, It'd be really nice if I had that method, right? We'll think about that later as a Christmas present to ourselves. This dot, if this is empty, then what should we do? Return null is the suggestion I heard, right? Wow, that looks like a convenient function to have. We should probably add that. Public Boolean is empty. How do you know if it's empty? This dot elements dot is empty. Right? Who would have thought that that would have been so useful that people implemented it? Right? What are you complaining about? Oh, return. There we go. Right. So if this is empty, now we're going to end up returning null. Oh, null. Wait a second. What if I had originally pushed null? I'm allowed to do that because of parameterization. How do you distinguish between the case where you push null and then you've popped out null versus you didn't push null and you're popping from an empty stack? Well, we kind of gave you the way to determine that by giving you this method here. So maybe that's enough. What's an alternative? What else could we have done here instead? You asked for something that doesn't exist. So one option is just to give you back null. Right? Another option is to communicate that to you. You screwed up. Right? You shouldn't have asked for that. How do I communicate that back to the calling function? I throw something at them. Right? New illegal state exception. Attempted to pop on empty stack. Now it's back on you. You catch it if you want. You do whatever you want with it, whatever you want with it. Right? But otherwise, it's not my problem. It's now your problem. I've thrown it back at you. Right? And that's exactly what we're going to get if we do not push null. There we go. Attempted to pop from an empty stack. Now that has me thinking here. Should we have allowed them to even push that element? Should we support nulls? I don't know. If x is null, we could throw that back at them, right? I could just return. That's what's called a no-op. No-op is a, or a noop is a no operation, right? We could just go ahead and say, screw it. I'm not going to do that. Right? Or I could say, throw new illegal argument exception. Right? This stack doesn't support nulls. Use a different stack. There. Two fine options there. Right? How do we know the difference? We document it. Throws on code. Actually, I'll show you something cool here. A link illegal argument exception if the element is code null. The reason that we like writing good documentation like this at link here, this annotation, means that I can now, when I generate the documentation, that becomes a hyperlink that takes me to that class, right? And gives me all the information about it. Right? It's existed there from the beginning. Right? Wonderful. Again, not a requirement for this course, but it is a habit that you probably should get into. Right? Writing good, nice, clean documentation. Right? For me, I like writing that good, clean documentation at the end. It's just because it kind of it fills that emptiness of being incomplete, right? If I don't have documentation there, it feels incomplete, and I go back and I make sure that it's complete. Right? Not that I'll ever read it again, but it's there at least. Right? Okay, so attempted to pop an empty stack, great. All right. Another potential issue. We're back to normal here, right? Push 4 things, pop 4 things, works. Push 4 things, pop 5 things. What's going to happen? I guess we already took it, and I misspelled empty, didn't I? Right? There we go. I guess we already did this. Sorry. Empty. There we go. All right. Can anybody think of another variation that we could add to our stack? For example, where have we seen stacks before? A program call stack, right? Where you have a function that calls a function that calls a function that calls a function, and you have stack frames piled on top of stack frames. Can you do that forever? Nope. Eventually, you run out of stack space. that stack space is limited to, say, 4 megabytes. What if we wanted to implement it so that our stack had a limit? Private int max size. Say that's 100. Right? Then what I could do here? Well, first of all, we'll still not accept nulls, but else if it's full, this dot is full. Right? I wonder how we will do that, right? Then I'll say throw an illegal argument exception, full stack. Right? Nope, we're not going to do that. So if we've got this convenience function of isEmpty, maybe we could have a convenience function called isFull that works how? If this dot, now a list doesn't necessarily have a predetermined limit, right? But if this dot elements hits our predetermined limit, this dot max size, then we'll return, yep, it's full. Right? What are you complaining about? Oh, dot size, sorry. There we go. Right. We could make that tunable. We could make a public stack constructor here that took in, say, int max size. Right? And instead of having that default of 100, we could say this dot max size is equal to max size. That gives you some flexibility, right? Then what we could do is we could say that the default is not 100, the default is 0, meaning that down here, this isFull method, if this dot max size is equal to 0, then we'll circumvent this entire thing and say, nope, it's never full. Return false. Else, return this. In other words, it's an unbounded stack. We're right back to where we started. But we're giving you the option, right? You can go ahead and set this max size. If you do not set a max size of 0 will imply no limit, right? So 0 equals no limit. It's what it's called an unbounded stack. It's only bounded by memory, right? Obviously, you can't. You'll eventually run out of memory on a computer at some point, right? Cool. We've got a lot of bells and whistles here already with a very, very, very simple implementation, right? So you can also have an option. Let's think about more optional operations, right? Sorry for the live stream. Well, it says it's only dropping 3%, so sorry if it's buggy today. I don't know why. The live stream keeps going down. Anyway, some optional operations would include peek. Right? So have you ever peeked at your presents? You didn't open them, right? Because then you'd get in trouble. But you just slightly open them, see what's in there, right? That's peeking, right? That means that you are going to retrieve, retrieve, but do not remove the top element. How could we do that? Same thing as pop, but peek. Right? If it's empty, then attempted to peek at an empty stack. Don't do that. Right? Otherwise, we will not remove. Instead, we'll get the element at that last index. Right? We're not removing it. We're just returning it. You can have a whole bunch of other things, right? Again, most of the stuff we've talked about here. But what happens when you pop from an empty stack? What do you do to impose it? How can you impose a capacity and give them give your user flexibility? How do you implement a stack? We've been using a linked list. Could you use an array-based list? Yeah. Let's think about how that would work, though. So if you've got an array-based list, is it efficient or is it inefficient to always be inserting, insert, remove, stuff, remove at the beginning of that list? That would be inefficient. Why? Because you're always forced to take everything and shift it down or shift it up, right? But what if you always worked at the other end? So this is not going to be an option here. Forget about that. What if you worked at the other end? What if instead your array looked like this? Right? Here's the index, 0, 1, 2, right? These are indices. And then this is the top, and this is the bottom. Right? It would be exactly the array-based implementation that we've just made. Right? You'd have a certain capacity here. And by the way, if you want to support a capacity, you could go ahead and switch to an array-based list because it'll never grow, it'll never shrink beyond what your initial capacity is. So maybe there's an argument for why you would want to do that. But anytime that you add something, you always add it to the bottom. So 23, 24, 7, and 6. Right? You always make sure to take from the end. Right? So if this is 3, then whatever that is, we pop that off the top. We need to keep track of the current index, but we can do it right? Just as efficiently. And I would argue that it's probably more efficient if you are going to have a predetermined and fixed capacity up front. That's going to be way more efficient. By the way, you can do this from both ends as well. We'll talk about that when we talk about DEX. Right? And you can still make it efficient even with an array-based list. You just have to be clever. I don't like being clever too much because then that's a lot of code. Right? All right. Questions on stacks. We'll talk about applications later. No? Then what are the other ones? I asked about this to the Omaha folks. Ever been to a store up in Omaha called Chippies? Have you heard of it? No, it's an Anglophile store. You go there, they've got a bunch of Doctor Who stuff and like foods and mostly candy from Britain. Oh, there's one in Lincoln now? Okay. There's a Chippies? All right. You could go there for high tea if you wanted to, right? So what do the British call a line if you have to go to Chippies and wait in line for your tea? They call it a queue. And that's what we're going to look at here, right? This is a FIFO. What do you think FIFO stands for? First in, first out. Why? Because you get in line, you're the next person to be served, right? No line jumpers. Make sure that you queue up, make sure that you line up correctly and that you're taking your turn. Remember, we're ending early today. Why? Because I want to go over and get some more pizza. Right?